Welcome back, ladies and gentlemen. So, this should be our last video for physical properties of matter. At this point, we've been talking about, of course, the kinetic molecular theory. We talked about phase changes. We talked about intermolecular forces. We talked about all these things build together to explain stuff we already kind of know about matter and how it behaves. We now understand how solids behave. That was the last video where we talked about the interconnection between the different properties of solids and their behaviors and all these theories and ideas that we've built up. So solids are done. Well, liquids, as I said last time, we got to do liquids, but we're going to cover that in the solutions unit, which is not the next unit. It's going to be the unit after that, just before Christmas. Then we got gases. Well, that's going to be the gas unit, which is the very next unit we're going to do. Okay, there's one thing that I want to cover before we get to gases. And that one thing is called vapor pressure. Now, the reason I want to cover that before we get to the gas unit directly is because vapor pressure, it involves gases, 100%. But it specifically involves the interaction between gases and their phase change, right? Liquids and solids are mostly incompressible, and they have a lot of specific features related to their specific volume or specific shape. Gases don't. Gases are weird. They have all sorts of ways they break the rules. Well, except the kinetic molecular theory rules, but that's a different thing. And as a result of this, the process of a gas condensing or a liquid boiling is weird. And so I want to talk about it in some detail before we get on to the gas unit directly, where all of these things are explored in a lot more detail. It's all going to be related to the intermolecular forces and the kinetic molecular theory, like all the stuff that we've been doing up until this point sort of builds towards this. All right, so let's take a look at what we're talking about. First things first, in the drive, you will see that there's some pages from our textbook that I've copied. They're under this teacher notes. You can read up a little bit about gases in there in order to get a little more information, okay? So you might have already read this if you started reading these pages for kinetic molecular theory, but now you can look at it into some more detail. So vapor pressure. All right, let's start with that. Remember, for a phase change, we want to either gain or lose energy. We talked about that, right? So condensation is pretty easy to explain, but vaporization is strange because there are two basic options. There's evaporation and there's boiling. And they both basically do the same thing. They both vaporize the liquid, turning it into a gas. But how it happens is strange. So in order for us to explore this, the first things first, we're going to need to define a bunch of terms. This is called front loading in education. We need to make sure we have these terms understood so we can explain everything, right? But first, of course, reminder, condensation, we're going to have a gas turning into a liquid, whereas for vaporization is a liquid turning into a gas, right? And then vaporization, as I just said, has got two different options in terms of what we call that. Okay, here's our definitions. There's a bunch. Gas. Okay, that one should be easy. One of the states of matter with no definite shape or volume. So it can be indefinite, it can be anything, basically. A vapor. Now you've heard the word vapor, but it has a special definition here. A special name given to a gas that is normally a liquid at room temperature. So for example, chlorine we would just call a gas because it's just a gas at room temperature. But water that's a gas we would call a vapor. So water vapor is because under normal circumstances, water will be a liquid. So if we have a gas of water particles, we would call it a vapor to indicate to the person I'm talking to, or this chemist is talking to, that this material is normally a liquid at room temperature. Why do we need that? Well, room temperature is pretty common in most rooms, hence its name, and it's pretty important. Being able to know what room temperature is and how it behaves is kind of useful for the purposes of being able to explain certain features and aspects of what's happening. So it's just a very common thing that we end up looking into. Evaporation is the process where energetic or fast particles escape the liquid once they reach the surface. Okay, so particles escaping the liquid, turning into a gas, when they reach the surface. Those are the key parts there. Boiling. The process by where particles are given energy, so bubbles of vapor form inside the liquid. Okay, we see our differences here, right? One of them is talking about the surface, and one of them is talking about in the liquid. Okay. Gas pressure. The force of a gas impacting on its surroundings. So right now, in this room that I am in, there is, of course, a gas because I can breathe. And this gas is pressing outward on all of the surfaces, on all the windows, on all the tables, all the ceiling, the walls, everything. It's also pressing on me. It's making a gas pressure. This gas pressure, of course, is a force. It pushes on things. Now, I'm designed to handle the gas pressure on Earth, so I don't have any problem moving around. But if the gas pressure got too big, I might find that it's very difficult to do anything. What else do we have? Well, we've also got vapor pressure. This is the force of a vapor on the surface of its liquid. Okay, now a vapor, remember, is something that's normally a liquid, right? So for example, water here is normally a liquid. The water vapor coming off of this, maybe through evaporation, is going to be pushing against everything because it's now a gas of some form. It's a vapor. So what these do and how they interact is important. Okay, but first, right, let's take a look at the key thing here. So for vaporization, particles must have enough energy to escape the liquid phase. Okay, that makes sense. Based on our understanding of how solid, liquid, and gas works, we understand, right, that we need to get enough energy to be able to break free or overpower the intermolecular forces so we can escape. So in order for me to go from a liquid to a gas, I need enough energy to make that transition. The difference here is only what they do once they get that energy. Here, they're escaping when they get to the surface. Here, they're making some kind of vapor bubbles underwater or in the liquid. So that's a small difference, but an important one. All right, let's take another look at this. Evaporation. We're going to talk about evaporation first. Evaporation, it happens constantly for all liquids, but it's very, very slow. Why is it slow? Above the liquid is air, and that air doesn't want to share space with the vapor. Remember, that would be the liquid leaving, right? The vapor in this case would be the water. So the air above the water doesn't want to share space. So the particles of air apply a gas pressure, they push down on the surface of the water. So it's kind of like the door to the classroom. When all of the students are in the class, there's a bunch of students outside the class, and the bell goes, and all the students in the class want to get out, and all the students out want to get in. Well, what happens? Everyone gets stuck at the door. The students on the outside don't want to back up because they want to get in, and the students on the inside don't want to back up because they want to get out. So you end up with this pressure at the door where both sides are pushing, trying to get through. The same thing is happening on the surface of any liquid. This water is being pressed down by the air above it, and that air doesn't want any water to escape. So the water should stay in place. I mean, assuming the air pressure is high enough, the gas pressure is high enough. So to evaporate, to escape the liquid, a particle needs enough energy to, 1, break free of the intermolecular forces, just like any other phase change. But 2, push aside the air. Right? There are 2 things the particles need to do. The particles need to be able to break free of the intermolecular forces. They need enough energy to pay off that debt that they have. And then once they've paid off that debt, then they still have to fight their way through all the oxygen. So again, okay, we'll try to go with an analogy here, similar to the classroom thing. We're all sitting on the tables. You need to have enough energy to be allowed to leave the spot in the tables. I end up talking about the crystal of the classroom, right? You're stuck in the table until you are released, until you have enough energy. The bell rings. That gives you enough energy to get out of the table, out of the chair. But then you go to the door and all those people are in the way. So even though you have enough energy to leave, you can't because people are blocking you. So that means that you've accomplished part A, but you haven't accomplished part B. And if you don't do both, you don't get to escape. You are still trapped. You can't leave the room until you get out. Please don't smash through the windows. But that's the basic idea. Whether or not you can escape depends on two factors. This is unique. Gases have this problem. Solids and liquids do not. The main reason is because of that whole indeterminate shape, indeterminate volume. Gases can expand and contract based on the situation around them. So this complicates things. And obviously, right, if there's gas above pushing down, it's going to change things. Now, okay, we can take this to the extreme. What happens if there was no air, right, above? If there was no air pushing down? Well, then this part doesn't matter anymore, right? If there's no air pushing down, then I don't care about this because there's no air I have to push aside, right? If there's no students waiting outside the door to stop you from getting out, you just walk out the door, no problem. So then this becomes the only thing you care about. But, barring the occasional astronaut in the class here, for the most part, we're not going to have that advantage. For the most part, we're going to be having the situation where air is going to be a problem and we have to push it out of the way. So what does this do for us? What does this mean? Okay, we got two things we need to accomplish. So we're going to break this down one piece at a time. First things first, to break free of the intermolecular forces. Okay, we know about this. We've talked about this when it comes to solids and liquids. So this is not going to be that unsurprising. Just like with solids or liquids, weak intermolecular forces makes it easier for energetic particles to escape. Strong intermolecular forces make it harder for particles to escape. Okay, that makes sense, right? Like if I've got very weak forces, then it's easy for me to break the connections, to pay off the debt, and to start making my exit, right? So in this case, if the teacher is very nice and says that you can get up and go get a drink whenever you want, like as if that would ever happen. But if the teacher did that and said, yeah, you can get up whenever you want, you have very weak forces holding you in the chair. So you can leave kind of whenever you want. You still got to come back. Got to do it. I'm not doing attendance during this. Who knows? Maybe you're not even here. But you can leave kind of whenever you want. Versus strong intermolecular forces where it's like if you so much as twitch and the teacher's like, what are you doing? What are you doing? Sit down. Right? Totally different. Totally different behaviors here. So here we see, of course, this is going to have very weak intermolecular forces. This is going to have very strong intermolecular forces, right? We've got water with hydrogen bonding versus chlorine with London dispersion forces. Now, we've talked about those at great length. We know how those work. Now, obviously, chlorine would normally be a gas at room temperature, but whatever. I'm still talking about the idea of how strong or weak it is. This is easy to escape. This is much harder to escape. Increase the rate of vaporization, decrease. Okay, let's think this through. Increase the rate, so that's the speed of vaporization. That's the big fancy word that basically means turning into a gas. So if you are weak forces, you will turn into a gas faster. If there are strong forces, you will turn into a gas slower. I don't think that's a surprise. I think everyone probably sees that and goes, okay, yeah, that makes sense, right? Like if I'm holding you in place really carefully, it's harder to escape. But if the hold is pretty loose, it's easier to get away. So that's the first part of this puzzle, right? And you'll notice all of these things are constant and depend on the material, right? Like it doesn't matter what else I'm doing to the chlorine. The chlorine's intermolecular forces are always the same. They don't magically change if I move my sample of chlorine from one side of the room to the other, right? They're always the same strength. So that means that the intermolecular forces here are going to be always the same. So it's a known value that we can work with, we can plan for. The pressure of the gas pressure, the pressure of the air pushing down, that's not always the same, right? Like if I had less air above my container, it wouldn't have as much force because there's less of it. If I had no air, there'd be no force at all. If I had lots of air, there'd be tons of force. So obviously that's going to be very different. But the intermolecular force part, that's constant, right? This is the part that's the most similar to liquids and solids. It's only this whole pressure of the gas pushing down part. That's the part that's weird. So let's take a look at that in more detail. We got to push aside the air. So pressure depends on the number of particles. The more particles I have, the more pressure I have. Right? Because pressure, again, if there's one student waiting to come into the room and all of you guys are trying to leave, well, that one student isn't going to really stop you. You guys will just go past them. But if there's like 20 students just crammed around the door, you can't get out because there's too many. So the more students, the more particles, the more pressure, the harder it is to get out. I think that makes sense, right? It's directly related. So less pressure, the vapor particles need less extra energy to escape, right? Because they always needed some energy, but now they need less extra energy, right? Beyond the normal for liquids and solids. More pressure, the vapor particles need more energy to escape. Again, remember, vapor means gas particles that are normally a liquid, so water vapor, right? So the vapor trying to escape here. So this will increase the rate of vaporization. This will decrease the rate of vaporization, right? So again, the more students I cram around the door, stopping you guys from being able to leave, the slower it's going to take for you to leave. Whereas the less students there are, the less time it will take for you to leave. You'll be able to escape a lot faster. I think that makes sense, right? So these two things are working in ways that are pretty logical. If I've got strong forces and a lot of pressure pushing down, it's very hard to escape because there's lots of grip holding you tight. And once you do finally break free, there's a bunch of guys waiting at the door to stop you from getting out, right? There's a lot of things in the way. On the other end of the spectrum, very weak forces, very little grip at all. And there's almost nothing blocking the way, so you can just get out no problem. So in a way, you can think of liquids that boil at a really high temperature. They're like a high security prison, right? There's guards, there's a lot of force, there's jail cells. You can't get out because other things are stopping you. Whereas a very easy boiling liquid is one in which it's like, well, it's just you can leave whenever you want. The door's right there. Go ahead. No one's going to stop you. No big deal. Right? So there are two things. How easy is it to get free of the other particles, and how easy is it to push the air out of the way so you can escape? So this pressure effect, as I mentioned, is dependent on the situation. Depending on the situation you find yourself in, you're going to have more or less pressure. All right, so if we just summarize all of this, to become a gas, particles must escape the liquid. This means they need enough energy to both break free of the IMFs and push aside the air. This means polar anionic compounds don't evaporate much because they have a lot of IMFs. Also, high pressure makes evaporation harder. So if I put my water inside of a pressure cooker that pushes down really, really hard, it's going to be harder and harder for the water to turn into a gas. There's a tiny little bit more to say here. Evaporation of a closed system. Closed system, what does that mean? I put a lid on it. That's all. Why is that important? Adding to the problem, as the vapor particles escape, they increase the pressure, right? One of those definitions at the start, vapor pressure is the pressure of the already evaporated particles pushing back down on the liquid. Wait, what? Okay, so analogy again. We're in the classroom, bell rings, it's time for you to leave. You've broken free of the intermolecular forces, but there's a bunch of people by the door. You finally push your way past all the people. You do. But the person behind you now has to push past all of those people and you, especially if you stop to talk to your friend who's coming into the class. You're in the way. Yeah, you got out, but now you're blocking other people's exit. The same thing happens with the gas. As the particles leave the liquid, they end up pushing aside the air, but then they become part of the problem. They gum up the works. They get in the way. Why is this critical? Because if I cover the system, if I put a lid on it, then the particles have nowhere to go. So over time, the area above the liquid gets heavier and heavier, or denser and denser. There's more and more particles in the same amount of space. The pressure goes up. There's more particles you have to push out of the way. If the lid isn't put on, then once the particles escape, they can just leave. They can go up into the air, no problem. But if there's a lid, they can't. If I left this here long enough, eventually all this water would evaporate away, right? And eventually there'd be nothing left. But if I put a lid on, if I seal it, well then eventually the amount of particles trying to get out, the ones that are left can't get past the ones that are already up here. They'll get in each other's way. They'll block each other off. That's it. That's the key thing. This is the reason why water bottles have a lid. I mean, that and then you don't spill them. But if you close the lid, that means that the water can't evaporate because there's no space for it in the air above the liquid. Eventually, there will be so many vapor particles above the liquid, nothing else can escape. Now, how many vapor particles you need depends on the context at hand, right? Like if I've got a lot of space, like I do in my cup right now, well, then it's going to take a lot of particles. I might even be able to evaporate all of it. But if this thing was mostly full and I only had a tiny little space at the top, well, then it would happen a lot faster that I'd run out of space, right? So, yeah, that's what we're dealing with, okay? There are two big things that we're looking at. Oh, right. This is called a vapor equilibrium. Equilibrium. So vapor, okay, we know vapor is, right? Vapor is gas particles of things that are normally a liquid, aka water vapor. And equilibrium means balance, right? Equilibrium is when the seesaw is sitting there perfectly balanced in the middle. So what we're saying is it's the balance of particles coming up and down, right? So that way they all are perfectly uniform, in balance with each other. This is why your sealed bottle of water doesn't evaporate. It will still be there when you finally pick it up. I don't know how many times we've got a bottle of water in the lost and found. I don't know why it ends up in the lost and found. But we find a bottle of water and it'll stay there forever because if it can't escape, it stays in there. Okay, so here's our basic summary. You got to break free of the intermolecular forces, same as normal, right? You got to push aside the air and the vapor. Right? And the vapor. We're adding one extra piece on there. Now, again, normally, if the container is open, the vapor pressure doesn't have that big of a deal because the vapor will just escape into the air and it will fly away. But if it's closed, it's a much bigger deal because the more vapor I add, I'm like increasing the amount of people clogging up the door. All right. That's evaporation. What about boiling? Oh my, we're not even done yet? Mr. C, who knew this was so difficult? Boiling. Boiling is actually pretty easy. Boiling occurs when particles inside the liquid have enough energy to form a bubble of vapor. This can only happen if the vapor pressure, the pressure of the vapor, is equal to the gas pressure of the atmosphere. So think of it this way, right? Down deep in the water, way down here at the bottom, there might be a particle. And as we saw with the kinetic molecular theory, particles can have a random arrangement of energies, right? I could have a particle that's really, really cold, but I could also have a particle that's really, really hot. And that really, really hot particle, well, maybe it's actually hot enough that it should be a gas right now. Like maybe it's water and there's a particle that's got 100 degrees Celsius energy. Well, it should be a gas. But it's trapped down here at the bottom. That means there's all this other water in the way. So like a gas, one of the defining characteristics of a gas is it doesn't have roommates. You can't be a gas if you got a ton of roommates. So even though the particle has enough energy to be a gas, if it can't get out, it's not a gas. It's still stuck. But what happens if that one particle has so much energy that it can just be like, oh, get away. I need space. I need my personal space. All of you guys back off. And it is so energetic that it just starts shoving the other water particles away. It forces them back. And it makes a bubble, a vapor bubble. That vapor bubble might only last for a few seconds, might only last for a blink of an eye. But if it's energetic enough, if it has enough energy, it could force that bubble to keep getting bigger and bigger. And that bubble might start to rise up through the water. If it can get to the surface, it's free. All it has to do is fight its way through all of the other liquid particles. And in order for it to rise to the surface, what has to happen is the pressure of that one particle, or let's be honest, a whole bunch of particles, but the pressure of those vapor particles have to be equal to the pressure of the air pushing down. Okay, back to our analogy. So we're saying that, the analogy isn't going to be perfect here, but we're going to try. So we're in the classroom, right? A bunch of people are sitting in the desks. The bell hasn't gone, so they're not allowed to leave yet. They haven't broken free of the kinetic molecular theory. But one of the students, they got to go early. They have a doctor's appointment, right? They've already broken free of the energy. They don't need to wait for the bell. They just need to get out. But they got to get past everybody. And there's all those people outside the door still. They're still in the way. They're still stopping the person from getting out. They have to push through them. And maybe those people outside the room, they're not really paying very much attention, right? They're on their phones, they're talking to their friends. Maybe they're being a bit of a jerk. They don't like that guy. So what happens? They got to push everyone out of the way so they can get through. In order for them to do that, they got to be as strong as all the people pushing back. The vapor pressure, the pressure of the particles trying to escape, has to be the same as the pressure of the particles trying to force them back down. The difference between evaporation and boiling is that in evaporation, we said that your particle needs to have enough energy to both break the IMFs and push through the air. With boiling, we're assuming that the particle has enough energy to break the IMFs by default. So the only thing left is push through the air. They only require one thing. So that's why this is some ways easier, because it's half as much requirement, because we're just saying it's already got enough energy. That's the assumption of boiling. Put another way, the boiling point is the temperature when the vapor pressure of a substance is equal to the external or atmospheric pressure. That is what the boiling point is. That is the temperature at which particles that are trapped underneath can escape, because they have enough energy to do that. They have enough energy to force the water out of the way and to force the air to let them escape. It's a lot of energy for the most part. So this is the difference here. Right down here we've got evaporation, right, where their particles are leaving at the surface. Over here we have boiling, where bubbles form deep under the surface, and then they rise up because they're energetic enough they can fight their way through all of the liquid. This is what one of those bubbles would look like. Now, in the example I said one particle. It's never one particle. It's never one particle. Around this red circle, we see water particles. They're fairly close together, especially compared to a gas. Inside the red circle, there are gas particles. There are vapor particles, vapor because they're trying to escape. And they push outward, right? They're all that whole, I need my space, get away from me, right? And as a group, they're pushing everyone away. They're making a hole in the crowd. And if they have equal pressure going outward as the air pushing down, trying to stop them from escaping, they'll get out, right? If the kid who got the call saying they have to go to a doctor's appointment and they can leave early, can get through all the people stuffed up in front of the door, they get to leave. They just have to have enough force to get through. And that all comes down to energy, of course. Now, what is the difference in terms of how this looks like? I mean, these are all static pictures. Let's do something a little dynamic. We saw this earlier. This is boiling. And the reason we know it's boiling is because it's at the bottom and it's floating up. I mentioned when we talked about phase change, most people assume that these bubbles are made of air. They're not. These bubbles are made of vapor. This is water in the gas form. So these bubbles, by definition, are 100 degrees Celsius if this was water. That's the only way these can work. They have to be the same temperature as the water would normally boil. So this is the reason why, this touching you would be bad, because it's boiling water. So what we're seeing here, right, is evaporation is the one or two particles that are already able to escape, just making a run for it. Boiling is where you give enough energy that lots of particles start to get ready to escape. Now, the reason why things are happening sort of randomly, right? Like, why isn't all the water just turning into a gas all at once and just going? Because, as we said, in the kinetic molecular theory, particles have a distribution of energies. There's only going to be a few that are really hot. There's going to be a lot that are pretty cold. So I need to give lots of energy, and random choices of which particles are going to gain the energy they need to bump up to the boiling level, to the gas level, to the vapor level. So we'll see something like this, where it's going to be random which ones turn into a gas and which ones don't. The only thing we can say for certain is that the ones that are currently turning into vapor were or are, I should say, rich, right? They have lots of energy for whatever reason. Maybe they had lots to start with, and they just got the last little bit they needed, right? Maybe they were over here in our example. Or maybe they were ones that were really cold, but happened to get a whole bunch of energy from the heating element in this case. We don't know. It's random. There's that kinetic molecular theory. So, as we can see, the atmospheric pressure is really important for boiling. Right? If the pressure is bigger, it's harder to boil. If it's smaller, it's easier. Since boiling occurs when the atmospheric pressure and the vapor pressure of a liquid are equal, any change in the pressure outside will produce a change in the boiling point. Right? If there's more pressure pushing down, it's going to take more effort to get out. More kids in front of the door, harder to escape. As atmospheric pressure decreases, so as it gets less pressure pushing down, the boiling point will go down too, because there's less pressure on the vapor side required to push past. So if I take kids away from in front of the door, right, if I tell them, guys, get out of the way, it's easier to push through because there's less of them in the way. Where was I? Since less vapor pressure is required to match the lower atmospheric pressure, less heat is needed in order to reach the boiling point, which remember, boiling point is when the two pressures are equal. So if the pressure of one is lower, then the pressure of the other one is lower, and that's going to take less energy overall. So, cooking. Hopefully you all do that at some point. Cooking on the prairies. At sea level, at a pressure of 1 atmosphere, aka on Earth, water will boil at 100 degrees Celsius. This means it will take you 10 minutes to hard boil an egg. Why? Because the way that boiling works, right, is that you've got whatever you want to cook, you put it in the water is heated up, and then the heat, the energy, is transferred from the water to the thing you want to cook. So if the thing I want to cook needs like a certain amount of energy to be cooked, and every second I'm giving it 100, then it's going to be like ding, 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 right? It slowly builds up, takes 10 minutes. Okay? Most of us are on the prairies, cooking on a mountain. On a mountain that is 4,300 meters above sea level, the pressure of the air is less. Half as much. And water boils at 81 degrees Celsius, which means that cooking the egg takes longer. There's a lot to unpack there. First of all, going up means less air. I guess that makes sense. You're getting closer to space, right? And space has no air. So if I go all the way to space, then there'd be no air. If I'm like halfway to space, there'd be half as much air. Okay, that's not quite true, but close enough for our understanding. So because there's less pressure pushing down, the water can escape more easily. It doesn't need as much pressure pushing up, right? It doesn't have as many kids in front of the door that they have to push out of the way. So instead of taking 100 degrees, it only goes up to 81 degrees. Well, right there. What that means, of course, is that, again, remember, to cook something, I'm giving that thing energy. So instead of every second I give it 100 degrees of energy, I give it 80. So instead of going up 1, 2, 3, 4, 5, maybe, to get up to 500, I'd have to go up like 1, 2, 3, 4, 5, 6, 7. Should have done the math first, right? It's the same amount of energy is required, but I'm giving it less energy per second, so it's going to take longer to reach the end. If it was a race, right, one guy's moving really fast, one guy's moving slower, so it's going to take him longer to get to the end. Logically, that makes sense. If I'm slow, but the race is the same length, it's going to take longer. All right, let's go crazy. Cooking under the sea. If you were 10 meters below sea level, the pressure is 2 atmospheres, so twice as much as it would be on the surface of the Earth where I'm standing right now. So the water will boil at 120 degrees. So it'll take me less time to give it enough energy. Now let's go super crazy. Cooking in space. In space, it's a vacuum, so there is no pressure at all. There is 0 pressure for fighting back. Well, a liquid boils when the vapor pressure pushing up and the gas pressure pushing down are equal. If there is no pressure pushing down, any amount of up is enough. So again, you got the note from the doctor, you get to leave early, you got to go to your appointment, there's nobody in the way, you just walk out. That's it, you're done. In space, water will boil at any temperature. above absolute zero. That's why you don't get liquid water in space, because the moment it's a liquid, there isn't enough force holding it together, it just escapes. Now, there is water in space. It's ice, solids, because solids are much better held together. That makes sense, right? Because there's more cohesive intermolecular forces, all those hydrogen bonds bonding it together. That makes sense. And why would it would not boil at negative 273? That's absolute zero. At absolute zero, all molecular motion stops. So it can't boil because it literally can't move at all. Now, space is cold, but even space isn't that cold. This is colder than space. The coldest space gets is negative 271, give or take. Pressure cookers. A pressure cooker are used to speed up cooking. By increasing the pressure inside the pot, you can increase the boiling point of the water just like when we put it underwater under the sea. This means you can put more energy in the water before the water boils away. This is one of the reasons why you might put a lid on the pot, because as you put a lid on the pot, the water evaporates, it builds up vapor in the chamber above the water. As the vapor increases in the amount, it pushes back down on the water in the pot, allowing it to boil or to delay reaching the boiling point, delay that balance of forces a little bit longer so you can heat the water a little bit more. Of course, eventually, the amount of pressure gets so much that it'll push the lid off. It'll escape from the sides or boil over. So it's not perfect. A pressure cooker is designed to be able to contain all that pressure. It's thick usually. It's very strong metals and ceramics, pottery. And it can hold everything together a little better. The higher the temperature at which the water boils, the shorter the cooking time, because the greater amount of heat will have already been delivered to the food by the time the boiling occurs. Yeah, we already talked about that. We get it, I hope. So everyday applications, right? Heating and boiling a liquid more strongly, a higher number on the stove, does not raise the temperature of the liquid, but it does cause the liquid to vaporize quicker. What do I mean by that? If I take my stove and I crank it up to the max setting, whatever it is, 10 on your stove, 8, whatever it is, if I crank it to the max, it doesn't mean that the water will get hotter. Water can only hold so much energy. How much energy depends on the pressure of the air pushing down. All that it does is it changes how fast I give it the energy. If I have enough energy coming out of the stove, I will reach 100 degrees. The question is just how long it takes, right? If I crank it to max, I'll reach 100 degrees faster, but I still only reach 100 degrees. If I want to get the water hotter, I got to apply more pressure to hold it down so that way it can't escape. So, in the analogy here, no, I got nothing. I can't figure out how to make that analogy work with the classroom thing. Sorry. So, the normal boiling point, the NBP, is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. So, for example, water is 100 degrees Celsius. And the reason we choose 101.3 kPas, we'll learn about that in the gas unit, but that's the official unit for measuring the pressure of the atmosphere. Well, one of them. We usually just use 1 atmosphere of pressure because it's the standard on Earth, and most of us are on Earth. Kilopascals, that's what the kPa is. That's useful when we want to talk about other planets, for example, because they have a different kind of atmosphere. For example, Venus. Venus has an atmosphere. Right? It's the second planet from the sun, almost the same size as the Earth, almost the same gravity. It's got 80 times the atmosphere of the Earth. So water that would boil here at 100, there would boil at, I don't even know, I'd have to do the math. It's going to be hundreds of degrees, hundreds and hundreds of degrees, because there's so much pressure squeezing down on it. When we first sent a probe to go and look at Venus, to take pictures and stuff, it didn't even get halfway through the atmosphere before it was crushed by the air pressure. And that was made of steel. It's pretty heavy. So different places have different pressures. We have 1 atmosphere here. We're used to it. We can handle it. So we're okay. So, assuming the pressure is constant, A low vapor pressure means that you have strong intermolecular forces. Low rates of evaporation. They're non-volatile, meaning that they don't easily turn into a gas, and a high boiling point. The opposite is true for high vapor pressures, right? Because this is another binary choice. And as we've discussed before in class, binary choices are just opposites. Whatever the first one is, the other one's the opposite. Now, of course, the problem here is you got to make sure to keep track of which one's which. Like high vapor pressure means a weak intermolecular force. Those two seem like they could be opposite right by themselves, and that's easy to get confused, right? So make sure you keep track of it, right? So like high vapor pressure, meaning that the pressure of the liquid pushing up is really, really big, means that there must be weak forces holding the particles together. Because the only way that the force pushing up can be so strong is if that particle is free to do its own thing, right? It's free to get that space it needs. If it doesn't have that freedom because all the rest of the particles are grabbing it and pulling it in, then it's not going to do it. Okay, so that's the basic idea behind vapor pressure. That's how we put all of this together. It's a lot, obviously. Evaporation was the most complicated of the two. Boiling was a little bit simpler, but it all comes down to these two competing forces, right? You've got first you need enough energy to escape from the liquid. Then you need enough energy to push past the gas above you, right? Two things, get out of the chair, get out of the room. Boiling automatically gives you enough energy to get out of the chair. But whether or not you have enough energy to get out of the room depends on how much the pressure is. Evaporation, eventually everyone will escape. Right? If I leave this out, eventually it will empty out. Why? Because the less liquid there is in there, the less intermolecular forces there are holding the existing particles together. So it turns in one of those like, if one person leaves, it's pretty hard because they got to beat everybody else. But the second person has got to beat everybody else -1. And the third person has to beat everyone else -2. And then the fourth person has to beat everyone else -3. Each time we make it a little bit easier because there's fewer particles holding everything together. Okay. Since the vapor pressure is an intrinsic property, the material, we can't just change it. So there's no tool that lets us directly alter the intermolecular forces. We can, however, affect how strong or weak those forces appear, or at least if the particles can overpower them with energy, aka with a graph. That's a lot. We're going to see what that looks like next time. I think right now I will leave it here because we've covered a lot of material here. So make sure to work through some of the practice, see what you guys can do, and I will see you guys next time.